Let's do a second example. This is a pretty classic one. I won't pretend to love it, but the trick we use here involving triangles shows up in some of the homework exercises. A conical water tank 10 feet high with a base radius of 5 feet sits on its tip. The tank is filling with water at a rate of 9 cubic feet per minute. When the water level is 6 feet, how quickly is the water rising? We are absolutely not going to get anywhere without a picture. I don't want to try to draw a three-dimensional cone, but hopefully this cross section will be good enough. What information are we given? We're given the base radius there. And we're given the height. We're told the tank is filling up with water. And the water level is rising. So we'd probably better give the water level a name to emphasize that the depth of the water in the tank is changing with time. Let's call it d of t. What do we have, if anything, that we haven't written down? We're told that we want to know what happens when d equals 6. We're not going to be able to use that for a while. We're given information about the volume, but that's not really something that we can label on this picture necessarily. With the understanding that we might have to come back to this, let's write down numerical information. And this stage will help clarify what is this 9. Cubic feet is a measure of volume. So this is telling you how the volume of the water in the tank is changing. Water is being pumped into this tank at a constant rate of 9 cubic feet per minute. What are we looking for? We're trying to find how quickly the depth is changing. So we're looking for the derivative of the depth, we're not given a time. We're interested in the derivative of the depth as the water reaches 6 feet. And now we need to try to do number 4. Okay, so we want to relate the information we're given to the information we have. We want to relate the information we're given to the information we're looking for. We're given information about the volume. We're looking for information about the depth. If we don't remember the equation for the volume of this cone, a quick Google search will refresh our memory. The volume is pi thirds times the radius squared times the depth. When I was drawing this picture, we didn't know we'd need this radius. But now that we do, let's label it. And the radius is also changing with time. As the water rises, the radius increases. Now here's the stumper. Calculus 1 and calculus 2 are derivatives with a single variable. But the radius is a variable and the depth is a variable. So now what? Well, now we stop and think. We're probably not giving you a bunch of useless information, but we have given you information that we haven't used yet. We haven't used the height of the tank. We haven't used the radius of the tank. And the trick here is similar triangles. So if we've got a right triangle like this, here's 5, here's 10, and then we cut the triangle like so. Here's R, here's D. This smaller triangle and this bigger triangle are similar. And what that tells you is that the ratios of their sides are the same. What was the problem here? We've related the volume to the depth. We're given information about the derivative of the volume. we want information about the derivative of the depth. Why didn't we just perform implicit differentiation here and get the derivative of the volume related to the derivative of the depth? Because this R was in the way. Because R is a function of t, and if we performed implicit differentiation, we'd get the derivative of R, and nothing in this problem helps us find the derivative of R. So that would just make the problem worse. But now, we can get rid of R. The volume is pi cubed times 1/2 d squared times d, which works out to pi 12ths. This 1/2 squared is 1/4. This third and the fourth give us a 12th. D cubed. And now that we recognized this, the problem's going to be pretty easy to finish out. But you could spend a fair amount of time looking at this picture before it occurs to you to try this. And that's just a feature of these related rates problems. You sometimes have to think about them for a long time. There's not really anything you can do about that. But now that we've written down the equation, we can differentiate. We're not using function notation here, but depth is a function of time. I used function notation up here. So when we take the derivative of both sides, we need to use the chain rule. This is a function cubed. This is the inner function. This is the outer function. We took the derivative. We stuck the inner function in it. Now we need the derivative of the inner function. And a good thing too, because this derivative is what we're trying to find. If we forgot to use the chain rule, the thing we were looking for wouldn't even appear. In particular, we're looking for the derivative when d is 6. And we've got the derivative of volume, which is 9. So 9 equals 3/12 pi over 4 times 36 times d prime. And if we divide both sides of this equation, d prime is 0.32 feet per minute.